Okay, let's dive into a core tool for any thermal engineer, a really powerful heat transfer formula.
This is the Zhukauskas correlation. Looks complex, right? But for engineers, it's absolutely essential.
To get why it's so important, we got to jump back to the middle of the 20th century. See, industry was growing fast, but the old formulas for heat exchangers, they just weren't cutting it.
So what made this new correlation the answer to this massive engineering problem?
Well, it wasn't just theory. This thing was built on decades of hardcore, real-world experimental data.
All right, history lesson over. Let's get our hands dirty and actually deconstruct this thing.
First up, the Reynolds number. This tells us how the fluid is flowing. Is it smooth or chaotic?
Next, the Prandtl number. It connects how the fluid moves with how it transfers heat. Super important.
And finally, the Nusselt number. This is the prize. It's what we're solving for. It quantifies the convection.
Now this is the genius part, the Prandtl number ratio. It corrects for temperature, making it crazy accurate.
Okay, theory's cool, but let's see it work. Time for a practical example.
Here's the setup. Hot engine oil flows over a heated cylinder. How much heat is actually moving?
First things first, you've got to calculate the Reynolds number. This will tell you the flow regime.
So for our problem, we get a Reynolds number of 125. That puts us right in the transition regime.
Based on that number, we go to the table and grab our constants, C and M. Simple as that. Now for the fun part. We just plug everything we found back into the main correlation.
And crunching the numbers gives us our answer, a Nusselt number of just under 156.
Great. So, why do we care about that? Because it lets us find the heat transfer coefficient, H.
And that coefficient gets us the heat flux, a make-or-break parameter for the exchanger design.
So why do we do all this math? Because this one calculation directly impacts the physical hardware. The big wins? It's super accurate for liquids, covers a massive flow range, and it's perfect for tube banks.
But of course, there are trade-offs. It's complex, and you need a good wall temperature, which can be tricky.
When you boil it all down, this math is the foundation for designing real-world shell and tube heat exchangers.
Which leads us with a big question. With tools like CFD, how long will these classic correlations reign supreme?